Part 5. The 9th today. Calvin. All right, so we are a little late today.
And some other symptoms was just being close by.
It's all right. It's raining. It's cruddy out. Couple things. So I sent out an announcement. So our exam was originally scheduled for Monday, this coming Monday. We're just going to go ahead and postpone that to the following Monday. We should have done that. I remember I did that last year as well. Because we introduced the R Markdown stuff, it kind of sets us back just a little bit on our normal progression. So in a week and a half is when we'll do our exam. That'll get us through this descriptive statistics section. Not only get us through, but it'll give you guys a chance to actually try it on your own, to practice it, homework assignment. So we'll have practice before we actually take the exam. That exam will be online, so it's going to go live. I don't know, probably 5 in the morning, 5:30 in the morning. It's whichever number I get in the AM, and then it's going to be due by 11:30 at night. All right, so part 1 would be the closed book part that you can think of if we were actually here in class. That's going to be your regular quiz, Blackboard test, mix of questions, fill in the blanks, multiple choice, multiple answers, maybe true, false, possibly. May have some calculations on it, so we'll go over some of the averages and whatnot. And then that one has a time limit. So when you start it, you have to finish it within the time limit. The other one, second part of the exam, is the markdown. That's the application part. So you'll be able to download the RMD file. The RMD file has the questions, just like we've had for these last 2 homeworks where I've said do this, do that. All right. There may be a question that you have to type an answer in, but that RMD file, you'll knit it to a PDF and then you'll upload it right to the site. So for those exams, it'll be in like 2 parts. So it'll have the quiz, all right, and then the second part would be the assignment, would be the part 2. That'll be that part 2. All right. Second thing, and Cody, you just reminded me, I have to do my roster today for that lab. I was panicking, thinking, crap, it's Thursday, I missed the deadline. Now, I'm sure if I was getting close, we would have received numerous emails. You're late, whatever. All right, second thing is quizzes. I posted 2 quizzes. These cover the data and biology stuff. I told you we typically have the quiz. So quiz 1, what I did was I saw that the quiz was actually kind of long with all the questions. So I broke it down. So the 2.1, that is variables, the type and scale. So here's a variable, tell me the type, tell me the scale of it. So is it qualitative, discrete, or continuous? That's our type. And the scale is nominal, ordinal, interval, or ratio scale. All right, so that's one quiz. You have, I think, 10 minutes, so it shouldn't, 10 minutes for 10 questions, right? And it should be pretty easy. You should be able to recognize that and not really have to think too much about it. The second one is the rest of the data in biology lecture, or the presentation, I should say. So it doesn't have the variable types and scale that was on the first quiz, but it does have things like rounding, the implied limits, right? Round this number to a specific place. What are the implied limits of these numbers, as well as like precision and accuracy, derived variables, and those figures. Like when you use which figures, or here's a variable, what figure could you use? Because that's, you'll see as we start getting to the stats and the analysis, first things we do is make a figure. We have to know, based on the variable types and how many variables we have, what is the appropriate figure, or what is one of the 2 or 3 appropriate figures that we could use. All right, so those are there. Those are out. I put a due date of Friday, end of the day on Friday to do those. That should be enough time to review your notes. A lot of the stuff, if you've learned it, you don't have to study a whole lot to get to it. We've all seen rounding, right? You've been doing rounding. My daughters have been doing rounding in grade school, so it's really nothing new. All right, so any questions? All right, so describing data. We're talking about means, variances, and so forth. We generated our data, so remember, if you close things, if you saved it, you closed it, very easy to open up and run that chunk again. That we have a AV1, AV2, and AV3 to work with. Right? So we started with the arithmetic mean. Right? This mean is sum of our values divided by n. Kind of gives us these. It's a measure of central tendency. Gives us our balance point. All right. It's going to be affected by outliers, by skew. When we have data points that are too small or too big compared to the rest. All right. Our calculations. I do think you should be able to calculate an average by hand. So, does anyone need to see how to do this by hand? Hopefully, add up the numbers, divide it by our sample size. All right. We learned how to do it in R. So the easiest way is just do the mean. So make your vector and then use the mean function. If you have missing data, you have to have na.rm equals t. All right, so I think I said we confirmed that our averages are correct. So we already had AV1, AV2, AV3. It was very easy just to say mean, parentheses, AV1, hit enter. Mean, AV2, enter, and so forth. And we got those numbers. Now what we're doing is the weighted average. All right, so the weighted average is when we weight our different values before we calculate the average. So the weighting comes with our sum. So instead of just taking the sum of the x, we take the sum of the x's that are weighted by whatever weight we assign it. All right, so normally we use this with frequency tables. All right, so with count data. I should say with discrete data. So here's a frequency table of AV3. First up, I want make sure your vectors are created. All right. Use our Markdown or RStudio R to make sure that this is the frequency table that you get. Did you guys get it? You have to go back and look up how to do it. So I know when I open this up, my global environment is empty. I know if I run it, R won't find AV3 at all. So I have to get it in. So I go to our chunk where we generated the data set for the lecture and I run it. All right. Why did we set the seed? Why did we set the seed? Yeah, so we're going to get the same number. So the numbers that we generate today are going to be the exact same numbers that we generated on Friday. All right, so we have the numbers. All right, it's in my environment. I can see that. And now I'm going to generate the table. So how did I generate the table? Table, that's our function, and then AV3. All right, and this will work because AV3 is a vector. All right, if this vector was in a data frame, remember we have to use data, $, and then our variable name. So I do that and I get my data table. Does this match what was in the PowerPoint? Hopefully. 18, 33, 27, 16, 2, and 4. Yep, okay. So you made it. That was just a quick check. All right, so how do we do our weighted average? So our weighted average can be done in R, or we could do it by hand, right? And what I'm going to show you is how to do it by hand. We're going to do it by hand, and then we're going to see how that applies in R. All of the YouTube video watchers, if you get motion sickness, probably close your eyes. Move this. Oh. All right. We are on the board. Check to make sure we're in enough. And that may also enlarge this. Tilted. But that'll work. Alright. So we start with our frequency table. This is the table that we started with. So what does this frequency table represent? It means we have 18 zeros in our data set. We have 33 ones in our data set, 27 twos in our data set, 16 threes, 2 fours, and 4 fives. So when would this be? Well, maybe we're counting up number of children that each family has. All right? And we're trying to figure out what's the average number of children that we have. Well, we have 18 families that have 0 children, 33 families that have 1 children, 27 have 2, 16 have 3, and so forth. Can we have half a child? No, all right? We're discrete data. So a frequency table is a valid type of display that we can use to summarize our data, all right? So our x's are 0 children, 1, 2, 3, 4, and 5. F is the frequency. This is also our weight. Because what we want to do is we want to have the average of x. That's what we're trying to find. What is the average of x? We want this column, but we have different weights. Yeah, we have 0, 1, 2, 3, 4, and 5, but we have 33 ones in that data set.
We want to account for that. We only have 2 4s in this data set. We want to account for that. So when we calculate this average, even though we're going to do regular arithmetic average, we're going to use weighted averages to calculate the actual x bar. All right, so what we're going to do is take these 2 columns and multiply them together. All right, this is also wx. All right, so I'm just going to multiply across the rows. All right, to get our wx. All right, and why do we do that? Well, it gets back to our equation. Our average, or frequency table, is the sum of wx over the sum of w. So what we've done is calculated wx for each of our values. This is basically our weighting. All right. Now what do we need to do? Well, we have to calculate the sum of our weights. All right. This number tells us how many data points we actually have in our data set. So what is the sum of this column? How many random data points do we generate? 100. So if we add up all of those numbers, we'll get 100. And then what we have to do is add up this column. All right. Pull out my calculator, add this up. I don't have all of the plates on. I got 163 today. I think that's about right. 163. Is that? You could. Good. Yeah, so I got 163. So I have those values. All I have to do now is plug each up. And as we showed my daughter the shortcut, which apparently this is not taught in schools. Right. 2 zeros, move the decimal place 2 to the left. All right. So our average is 1.6. Yes, she was doing long division. Why are you doing that? That's how we're taught. All right, so that's our average. That's our average x, and it should kind of make sense. If you look at just 0 to 5, you think our average is someplace around here, maybe right at 3. All right, but then when you look at the weights, you can see, well, I have many more families that actually had smaller, fewer kids. Well, this weighting is going to bring our average down, all right? And if you think about it then, and think about an average or a weighted, a balance point of our histogram, your pretty big hump here and then a longer tail there, we're going to be more down below where the peak is of that histogram, just to kind of get balanced just right. All right? So can we do this in R? Yeah, we can. We can use the weighted mean function, okay? So let's see how we do that.
And as I get ready to do this, oops, hold on, let's go to the next. I'm going to make a disclaimer to say that this is not the preferred method. When we have frequency tables like this is not going to be the method that you should use. And you might ask, well, why? Why not? It's because if we're generating summary statistics, we also generate a measure of dispersion. And we don't have an equivalent weighted dot variance function or a weighted dot standard deviation function. We have to do things separately, and I'm going to show that to you next. All right, so our function is weighted dot mean. That is our function. Weighted dot mean. And we're going to pass it two different vectors. We're going to pass it a vector of values. That's our data point. And then we're going to pass it a vector of weights. These are our frequencies. All right, so that's why I labeled our columns in that frequency table X and F. F is our weights, X is our data points. All right, so we have our frequency table here. We did it, we looked at it, and I did that so you can practice table. That's okay, they can see that we're up here. Thanks for that. So we have, we did this so we can see what we're looking at, all right? Because sometimes if you have a missing value, let's say if we have a missing 4, all right, that gets left out of the table. It's not going to list 4 and then 0. It just gets left out. So when we pass it a vector of values, we're going to utilize our table here, all right? So we're going to calculate the average of F3 using weighted dot mean using the weighted dot mean X comma F function. All right. So here, X and F are vectors. All right. So what we can do is create our own vectors. So our vector of 0, 1, 2, 3, 4, and 5. We can create our vector of our frequencies, so 18, 33, 27, 16, 2, and 4. Or we can do this all in the weighted dot mean function. This table is small enough that I am just going to create these vectors in the function. All right, so how do we create the vectors? Well, we use the C. The combine function, all right? We combine our data points into a vector. So our weighted dot mean, we're going to pass it the X values, our actual data values that we recorded, and that data was number of children. So our vector is 0, 1, 2, 3, 4, and 5. Was there another easier way to do it, or was there another way to do it? Yeah, you can use 0:5 to represent 0 to 5. All right, you can do that. You can use the sequence SEQ function to generate a sequence between two numbers with, based on, distances between them. We'll see some of that. But I think the easiest one for the small table is to do 0, 1, 2, 3, 4, and 5, and the combine function. And then we do our vector of frequencies. So 18, 33, 27, 16, 2, and 4. All right, so we passed it the vector of x's, a vector of frequencies. All right, and then what R is going to do is basically exactly what we did on the board. It's going to multiply each of these x's by its weight. It's going to add up all of those values, all of those products, all right, to get our sum. And then it's going to divide by the sum of that vector, so our sample size. So when we run it, we get 1.63, which is exactly what we calculated. It's exactly what we calculated. Do y'all get this? All right. What's this other way? I'm going to go back to the board. All right, so the other way is to convert this frequency table into a vector, into a single vector. We already have it. This is AV3, all right? But we're going to take this table and make a vector. How do we do it? So we have a couple different functions, a couple different ways that we can do it. All right. So
convert a frequency table to a vector. And we're going to do that several times throughout the course. All right? So we have this frequency table. What we want is a vector of the data. So question 1, what is the data that we want to vector? We want the x's, right?
Hey, Descriptive
So
gets high.
the data are the x's. All right? That's what we want. We don't want the x. So the way to think about this is that this frequency table was generated using the table function. And that table function basically took a vector where we had 18 zeros right in a row, and then 33 ones right after, and 27 twos right after that. All right? And so on until we got to the end. How do we generate that? Well, once we know that the data are x's, then we can use something called the rep function. Alright, so this rep function is going to repeat the x It's going to repeat x times times. All right. So example here, we're going to start with the 0. All right. So we're going to use rep 0, comma times equals 18. So what this is going to do is repeat 0 18 times. We're going to repeat 0 18 times. This is equivalent to rep 0, comma 18. So we don't have to actually write times equals. We can just do x, comma, and then the number of times that we want to repeat it. All right? Now what we want to do is save this as a single vector. All right? So the way we can do it is start to combine it with the C function. And then have our repeat function appear repeated. So we can do C rep 0, comma 18 and close our parentheses. And then a comma. Rep 1, comma 33. All right, close it and then comma. Now, I haven't finished it yet. But what we do is the first thing we do is, so the C is combined. So what we're going to do is we go inside the parentheses, rep makes a vector of 18 zeros. And it makes a vector of 33 ones. And then we're going to make a vector of 27 twos. 27 twos. I'm going to continue on the next line. And then we're going to have a vector of 16 threes. And then we're going to have a vector of 2 fours. And then we're going to have a vector of 4 fives. Where's that? And we're going to close it. So the rep is going to make our vector, and we're going to say here are our vectors, our 6 vectors, and then the combine is going to take all of those vectors and combine them into one single vector. And we're not going to be done. We can do A, B, E. So we take the x's, we're going to repeat each x, whatever number of times is in that frequency, and then we're going to combine all of them into a single vector F. All right. So go ahead and do that. And then once you get Av4 in, calculate the mean of the F4. You should have exactly the same mean that we've already calculated. All right. Yep. We need this vectors. We need to be able to create these vectors in order to calculate standard deviation or variance, confidence intervals, and also to do goodness of fit tests. So some of the goodness of fit tests actually needs the vector. All right. I'm gonna move our. Actually, I'm gonna shrink the size of our image and then move that in. C on the outside.
It starts with the C.
It starts with a C. Starts with a C, and then the reps are inside of that C. Back. All right, so I'm going to call AB4. Make my C. I'm going to rep my vectors 0, 18. Rep 1, 33. Rep 2, 27. Rep 3, 16. Rep. Oops. Rep 4, 2. And rep 5, 4. All right, so if I run this, I should get AB4. All right, and then just to confirm, we're going to calculate the mean of that. I got 1.63, just what we wanted. Get that? All right. Things that can go wrong. I would probably make a note, because you'll probably go back to this presentation. Say, oh, how do I do that again? All right. You can make a note. Things that can go wrong. Parentheses. Big time. All right. Fortunately, in R Studio, it can show me where my parentheses was closed. So if you do it, I can see on mine, it's barely up here on the screen. It's like a little bit shaded, like a highlighted background of that very first parentheses. All right? And I've got parentheses that you can see each one closes appropriately. And you can see if you go, whichever one you go to, it says whichever parentheses it's associated with. So we need parentheses for the rep function. So 2 items inside the rep function. And then we need the parentheses for our combine function. That's a common mistake. A less common mistake are the commas. So you do need a comma before each of our rep functions. And it basically is just saying, here's the first vector that we're going to create, here's the second vector, here's the third, and so forth, and then we combine all of those vectors together. All right, not terrible, right? All right, so we did that. All right,
And I'm just going to jump ahead real quick because that is in here. Here it is. Make a vector x using C and use the rep. So we use it again, all right? And we'll go over it again just as a reminder. Just as a reminder when we get there. All right, let's go to the rest. So are we going to do weighted averages by hand? Probably not. I think we'll just use R since it is online. But we do, I mean, I have it as homework to give you some practice. Kind of really drill home the idea of how we calculated the means. Because if you understand how to do it by hand, then you understand what you need to do with the R functions. So either make your vector or use the weighted mean function. So that's kind of has always been my approach. If you understand the equation of on how to calculate these things, then the R functions typically I should say, to me it makes a little bit more sense. All right, so that was the arithmetic mean. There are other means out there, including the geometric mean and the harmonic mean. Are we going to calculate these? No, we're not. We're not. But you could encounter them at some point. And in certain cases, certain types of data, you do want to use them because those means are the appropriate ones to use. So geometric mean, what is it? Geometric mean is basically taking the product of all of our values and then doing a root, an nth root, so the sample size root of it. All right. We would use this if we are working with data on the exponential scale. You might not realize that you are actually calculating the geometric mean, because normally if you have data on the geometric scale, you tend to plot it on a log scale. You take your data and then you calculate the logs. And then for the logs, that's what you plotted on the figure. That's typically what you take the average of. Well, that is the geometric mean. Because if you take the log of this geometric mean, you get the arithmetic mean of the log of your data. All right. Examples, serial dilutions. Right? You might say, what are serial dilutions? It's where you do, let's say, a 1 to 10 dilution, and then you do a 1 to 10 dilution of that, and then a 1 to 10 dilution of that. So you go, so your dilutions proceed, 1 to 10, 1 to 100, 1 to 1,000, 1 to 10,000, 1 to 100,000. If you work with those, you're dealing with, 1 over a couple thousand, 1 over a couple tens of thousands, and so forth. But if you take the log of those values, now you're working at 1, 2, 3, 4, 5, 6. All right, so it makes it very easy. Who uses them? A lot of the micro and molecular biology would use them. All right, so trying to figure out how many bacteria are in a culture. All right, they make serial dilutions and plate the culture, and once they get down to a dilution where they can actually count the plaques, now you've generated population size. That is our exponential scale, right? And it's estimated using these serial dilutions. Antibody titers. We're hearing about all of those now, right? Antibody titers, those are serial dilutions. Anytime we have data that spans several orders of magnitude, we should also use it. So I just pitched some yeast in a wort, all right? If I'm interested in yeast population size in that wort, depending on what I started with, I can end at different population sizes that vary on orders of magnitude. Maybe I have several hundred billion of yeast in one container, but I only have, let's say, 1 or 2 billion in another container. Those are orders of magnitude. And the orders of magnitude we're talking about numbers where you have like single digits and then double digits and triple digits. All right, so tens, hundreds, and then thousands. Those we would use geometric means for. And also population growth rate. So if you're doing some sort of ecological study and you're estimating growth rates, you're going to probably need to use geometric mean. The whole point of the geometric means is that we tend to compress the ranges of our data. Right? So if we realize that we are not normal, that our data are not normal, it could be because we're spanning several orders of magnitude. Taking a log might fix that, and that then gives us our geometric means. Harmonic means are the averages of the reciprocal of the reciprocals, or the reciprocal average of the reciprocals, I believe. All right. The only time you really use it is if you're doing rates. rates. So speed. Right? You've seen the problem. Probably on SATs or ACTs, they say elephant started here, traveled along the square, and traveled 5 miles per hour, and then it decided to jog at 10 miles per hour. Right? For the next leg, the longer leg, and then it slows down back to, let's say, 3 miles per hour because it was tired. And then the question would be, what is the average speed? And it's kind of a trick question because you have to recognize that we're doing rates and you need to use the harmonic mean in order to calculate that average. Are we going to do that? We're not. All right, we're not going to do that. So, but I do think you should recognize when would we use each of them. The most common mean that we use, arithmetic mean, unless you're working in like a micro lab or an immunology lab and you're doing a bunch of serial dilutions, then you're going to use geometric mean, or as I said, you just take the log of your data and then you're right back to the arithmetic mean. Do you remember that question on any of those exams? Trick question. Trick question. I saw it on the GRE. I thought that real, like taking 5 plus 10 plus 3 and taking the average, that was one of the answer choices. I thought, that's not, no, they're going to trick you. All right, so what are the relationships between these? Arithmetic mean is going to be the largest, followed by the geometric mean, then the harmonic. So, if you calculate the harmonic mean and someone says, wait, you used the wrong type of mean, is that going to change your answers? Yeah, it will change the answers, but if you know the relationship, and if you were already saying that the means were, one mean was smaller than the other one, it's really not going to change that relationship. If you use the correct means, everything's going to shift accordingly. So the largest mean that we'll see is arithmetic, geometric means next, and a harmonic mean. And all of these things act to kind of compress ranges. All right, what we'll do is stop here. On Friday, we will start with the medians. Medians are pretty easy. There is an R function to calculate the medians, and we use medians and quartiles and stuff to generate box plots in R, or I should say, R uses them to create box plots. We're not going to create any of them by hand, but for the medians, I'm going to show you a quick and easy way to find medians and quartiles, first and third quartiles. So we'll do some things on the board. I'll write some stuff out, and we'll do that on Friday. All right? All right. You guys have a good one. If you have any questions, please email me. Don't forget about the quiz. Due at the end of Friday. Shouldn't be terribly difficult.
I don't need to take an appointment with you.